Hi everyone. In this video we're going to talk about how to find the area under a curve. To get started, I thought it would be good to start out with a problem for why we care about this and what kind of a situation might motivate us to look at how to find the area under different types of curves. So let's start out by assuming that we have a function. We're going to call this f prime of x. So we're talking already about a speed or a velocity function. Let's use a practical real-world example. Let's say that you're driving in a car and you are driving a consistent speed, we'll say 50 miles an hour. And so if you're going 50 miles an hour the whole way on your trip, and you want to know after 2 hours how far have you traveled, that's a fairly straightforward problem to take a look at. You're going 50 miles an hour for 2 hours. You've traveled 100 miles. And what you're actually finding there is you're finding the area under the rectangle here. Now, a rectangle is not a hard geometric shape to find the area of. We know that you can find the area of a rectangle by looking at base times height. But what we're actually finding by finding the area of the rectangle is we're actually finding the total distance traveled, which is your speed, 50 miles an hour, times the 2 hours that you traveled. This is not a very interesting example, but it is one to think about because I think we can practically think about a situation where you're driving about 50 miles an hour, the same speed, at the same time. Now, that being said, when you drive a lot, sometimes you speed up a little bit, you slow down a little bit, so your curve doesn't always look like a straight rectangle. It actually might look a little bit more like this. This might be a little more realistic. So when you're going 50 miles an hour, you're going about 50, and then you kind of speed up a little bit, and then you realize you're going a little faster, you kind of slow down, and then you speed up a bit, and then you see a cop, and so you slow down or something like that, and then you kind of level out, and maybe at some point you kind of, this might represent you stopping for gas or something like that, and so your speed goes all the way down to 0. But again, we're still talking about a speed, so we're still talking about f prime of x. And so the question was, in this kind of a situation, might be how far did you travel? But for a curve like this, finding out how far you traveled, which is talking about the area under this curve, that's a much tougher situation to look at than when we were talking about a rectangle. That's because we know how to find the area of a rectangle pretty easily. So a good question to ask then is, what if we have a real-world context that doesn't just use a rectangle? What if it uses some crazy curve like this? How could we find how far we've traveled? And the area, we can still find the area under the curve by actually approximating. And so that's what we do commonly in calculus. This is a common technique, is to look at the area under the curve. We're actually going to estimate the area under the curve by using different rectangles. Okay, let's look at another situation real briefly here. Let's say you have a situation where you're going a set 50 miles an hour, and then you speed up consistently, and then you slow down consistently, and now you're going about 40 miles an hour for a while, and then you come to a complete stop. Could you find the area under this graph using some other geometric methods you might have seen in your past? One thought you could have is try to split this up as here's a triangle, here's a rectangle, here's some different rectangles with a triangle involved in there somehow, and lots of different shapes that you could break everything down into rectangles and triangles. And that's not a bad thought. We try to do something like this when we're finding the area under a graph or under a curve, but instead of trying to break it down into a bunch of different triangles and rectangles, we're just going to use rectangles. It's not hard to find the area of a rectangle, and so that's what we're going to do. We're going to take any kind of curve like this. I'll just start out with one that, here's a curve that's strictly increasing, so it's going up to the right. And let's say we want to find the area under this curve from a point A to a point B. So I'll just say we're trying to find this shaded region right here. Definitely easier said than done. But what we're going to do is we're going to approximate the area here using rectangles. And so I'm going to go ahead and draw in some rectangles in here. I'll use a different color. Let's go ahead and use blue. And I'm going to draw in rectangles here that look like this. So here's one, here's another one, there's a third rectangle, and there's a fourth rectangle. And I've drawn these in here like this specifically on purpose. I want you to look at where each of the rectangle crosses or intersects with the graph. Notice that I've intentionally drawn it so that every rectangle is intersecting the graph up in that top left corner. Okay, I could draw some in red that would look like intersecting the graph up in the top right corner, but it would look a little bit different. It would look something like this. So now notice that every rectangle in red is actually intersecting the graph up in the top right corner of the rectangle. So if we were looking at the blue rectangles here that I have, they intersect the graph in the top left corner. We're going to use this notation to talk about the blue rectangles. We're going to call it L4. Now the reason we're using L, hopefully this is fairly obvious, is that where the rectangles cross the graph is in the top left corner. So L for left. And if we were using the red rectangles, those red rectangles actually all intersect the graph up in the top right corner of the rectangle. We're going to go ahead and use R4 for the ones in red. And when we find L4, basically we're going to add up the areas of the 4 different blue rectangles. When we find R4, we're going to add up the areas of the 4 different red rectangles. So to find the areas of the rectangles and to estimate the area under the graph, we need to remember how to find the area of rectangles. And I'll go ahead and break this down a little bit more. Let's go back to that same graph that we just had, or similar at least. Hard to hand draw exactly the same graph. Let's say that we have these 4 rectangles right here. Okay, we need to know what is the width and the height, or you might call it the base and the height for each of these rectangles. So this rectangle right here, we'll call it rectangle number 1, has area of the base down on the bottom, which we'll call delta x, times its height. Now its height, we're going to talk about this as being an output value. It's actually an f value. For now, I'll just call it height. Okay, or you can even call it height 1, because they're going to have 4 different heights in here. Now on the bottom here, for the second rectangle, we're going to also have delta x. That's going to be the same kind of width for each of those. In fact, this is going to be true for all of these, is that you need to have the same width for every rectangle there. So I'm just going to call it delta x for all of these. This is going to be the same width now. The heights are going to be different, and so in general, if you want to find R4 or L4, or it doesn't have to be 4 rectangles, by the way, I just use that as kind of a nice number. It could be 8, it could be 10, it could be however many rectangles you want to use. It could be 50 for all we care. But R4 is going to look like this. You're going to take delta x times an output value. In that output value, if I go back, the output value of the first rectangle would be kind of right here, because you look at where that first graph, or where that first rectangle crosses the graph or touches the graph, it touches up in the top left corner. So here's your x1. Maybe I shouldn't put all these little delta x's down the bottom, but your x1 is talking about the function value where you get your height for the first rectangle. For the second rectangle, you're going to be using x2 right there, and f of x2 is going to give you the top left corner, and that will give you the height of the rectangle. For the third rectangle, you're going to use x3 right here on the left side, because that's going to give you, using that x value is going to give you the height of the third rectangle. And for the fourth rectangle, you're using x4 over here, which is going to give you the height of that fourth rectangle. So if we were using this an example, I shouldn't call it R4, this is actually L4 in this example, because of where my rectangles touch the top left corner. So this is actually L4. And the area of each of those rectangles all added together is going to look like delta x times f of x1 plus delta x times f of x2 plus delta x times f of x3 plus delta x times f of x4. Now, you might notice something pretty quickly here is that I didn't have to write delta x 4 different times. I could have also just written this as delta x times, and then put parentheses, factored that out, that delta x out. So then I have f of x1 plus f of x2 plus f of x3 plus f of x4. And I could write it like that as well. And what's important here is that the x1, x2, x3, x4, those values are on the left side, or the left end point, I should say, of each triangle, or not triangle, of each rectangle. So the values of x1, x2, x3, x4, those are values that are on the left side of each rectangle because we're using a left-hand sum. That's why we're calling it L4. So we'll look at an example in the next video that you can take a look at, but this is kind of the formula you're going to want to think about using for L4 every time. This delta x here is talking about the base or the width of each rectangle, and then you have the different heights of the 4 different rectangles by finding the f of x1 and f of x2 and f of x3 and f of x4. Let's say we were finding R4 in a second. It would be almost the same thing. I want you to think about how things would be different. Let me go back to my picture over here a second. Actually, I'll go back all the way to where we had the red rectangles. How would things be different in the formula if we were using R4 instead of L4? Okay, take a look at that for a second. Look at where your x1 and x2, x3, and x4 values would be. What can you tell about delta x? How are things similar? How are things different? Let's go back and take a look. If we had a function that looks like this, and we were going from, what was our input? We were going, did we even label it? We just said A to B, I think, right? So let's go from A up to B. Now, in this case, our x1 and our x2, x3, x4 would actually be values that aren't on the left endpoint of each rectangle. Now they're values that have to be on the right endpoint of each rectangle. Okay, so now x1 wouldn't be at the very beginning of the first rectangle. It would actually be at the end of the first rectangle. x2 would be on the right side of the second rectangle. x3 would be on the right side of the third rectangle. And where B is, I'll go ahead and erase B, and we'll call that x4, would be on the right side of the fourth rectangle because we are using a right-hand sum. Now you're still going to have delta x in the same way that we did before, so it's still going to be delta x times a whole bunch of stuff, but what you have in parentheses now is going to look like a different x1, a different x2, a different x3. I'm still going to call them x1, x2, x3, x4 because there's still different x values that we have, and there's still 4 of them, but they're actually going to be in a different spot than if we had been doing L4. We'll see that in an example in the next video. So you would still get something like this. Now, last thing for this part, or for this video, is that if you look back at the L4 example that we looked at, in this case, you'll notice there's a little bit of area above the rectangles that is actually under the graph that we are not including when we find L4. That means that there is area missing in our calculation. So the estimate that we find by doing L4, this is actually an underestimate, because remember, our goal is to try to estimate the actual area under the curve. But here there's actually area missing that we didn't include in our calculation, but we should have included if we were trying to find the actual area under the graph. If you go over to here to R4, look at the rectangles on R4. There's actually too much space that we're counting on the top of the rectangles that we are including in our calculation here, but we shouldn't be, because remember, we're only trying to find the area under the curve. So with this R4, there is actually too much area. This is actually an overestimate. Now, it's not always true that a right-hand sum is an overestimate and a left-hand sum is an underestimate, but that does happen to be the case in the graph that I've drawn here. We'll see how that plays out in the next example, in the next video, and sometimes it'll be the other way around, but we'll see that when we look at a specific example here in a minute. Okay, hope you've enjoyed this video.